Here we've got another Lewis diagram, nitrogen, carbon, and chlorine shown nicely here. It's called cyanogen chloride. Now officially the name should be carbonitratic chloride or chloroformonitrile, but as you can see, the cyanogen is a lot easier to say. So most people will just call this cyanogen chloride. And first of all, the compound itself is interesting in that it's a rather dangerous substance, toxic. In fact, it's even considered to be a dangerous enough compound that you have to report any production of this. It's used for things like making organic compounds. It's very useful for that, but still, because it does have a chance of being used for a chemical warfare weapon, generally if you produce this, you should end up indicating that you're making it and its purpose through the organization of the prohibition of chemical weapons. It's nice that there is an organization like that, one that's trying to prevent using chemicals for weapons in warfare. Let's do the Lewis dot diagram of this. Here we go. We've got a nitrogen, carbon, and chlorine. Of course, we know our Lewis dots are pretty easy to figure out for our compounds. Here we've got a nitrogen, which is 5 valence electrons, and we have just a single carbon with 4 valence electrons. And then we've got our chlorine with 7 valence electrons over here. This has got a third energy level, so the chlorine will be a larger atom than both the carbon and the nitrogen, which will be approximately the same size there in the second period versus the third period for chlorine. So let's see how many electrons we have to play with this compound. We add them all together and get ourselves 16. Whenever you do a Lewis diagram, double check this, because if you get this count wrong, you're going to have to go all the way back to the start. 5 plus 4, 9, 7, 16. We're there. That's our first step, is count the valence electrons, the electrons in the outer energy level. Next step is to put in bonds between our atoms. Now they've given us the structure as carbon being the center, which is pretty typical. Put a bond between the nitrogen and the carbon, and of course I'll put the bond between the carbon and the chloride atom. We're making a covalently bonded molecule. There are 2 electrons in each one of these lines, so we can subtract 4 from our count and realize that we have 12 valence electrons left behind. And I've got my valence electrons here in pairs, 2 electrons per orbital. So I'm going to pick up a pair of electrons, unshared, and I'm going to put them on the surrounding atoms. Now these atoms are going to have their octets. I've got 2 here, and let me complete that octet by grabbing this pair of electrons and pasting them on the nitrogen. We do the outside atoms first. That's the best way of doing these things. So I've added 6 more electrons for this nitrogen. It has indeed the octet, which has got the lowest energy level. We've got this energy level now filled with electrons. 3 of these floating about the nitrogen, and 2 as this shared pair that bonds the nitrogen and carbon together. These protons of carbon and these protons of nitrogen are being attracted to that pair of electrons. Let me do the same for chlorine. I've got my pair of electrons there. Here we go. Another pair of electrons on top, and I'll get my group here and put them on the side. And I'll take this and copy it and then paste right here. And my chlorine now has its octet too. So we've used up all 12 electrons, 6 and 6, so there are no valence electrons left. And unfortunately, our carbon here is missing its octet. It's got room for 4 more electrons, and in our rule for Lewis diagrams, we decide that it's best to take a pair of electrons and share them, because this carbon is going to be attracted to these electrons. We put that there, and we make another double bond here. This would be sort of logical for us. And now we'd see that we have an octet 2, 4, 6, 8 around the nitrogen, 2, 4, 6, 8 around the carbon, and 2, 4, 6, 8 around this chlorine. If we were to draw circles around these, we would say everybody the lowest potential energy. And I'm going to delete these 2 right now, and instead this pair of double bonds is a little bit shorter than the previous ones. If we went right here, this would be a Lewis diagram that would be acceptable if you were just say make a Lewis diagram. However, if the question also said come up with the most likely structure using formal charges, then you'd have an extra step to work on. Because if we look at this in terms of formal charges, which sort of indicates the best arrangement, because there's a number of different ways we can get octets here. If you want to have the best arrangement, and if you're asked for formal charges, then what you would do is try and figure out the formal charge on each one of these atoms to see how they're dealing with these shared pairs of electrons and unshared pairs of electrons. End up drawing circles around each one of our atoms to see the electrons that they control. So I'll draw around my nitrogen. This circle shows that it's controlling 1, 2, 3, 4, and it's got one of these shared pairs and one of these shared pairs. It's controlling 6 minuses, 6 electrons. But nitrogen typically ends up having a structure of 5. So this nitrogen has in effect an extra electron in terms of formal charges, so it would have a -1 for its formal charge. Are just sort of saying, okay, this is a little bit unusual. The nitrogen has an extra electron that is more than we would expect. We'll do the same thing for our carbon, and again I'll get my drawing and get my circle going around it. I'll figure this one out also. And this is pretty good because carbon typically will have 4 electrons around it. In this case, 1, 2, 3, 4, half of each one of these shared pairs, so it has a formal charge of 0. We know if we're doing formal charges correctly, the formal charges will add up to the charge of the molecule. In this case, it's a neutral molecule, so we know this chlorine is going to have to be a +1. If we're not getting a +1, we know we did something wrong. And so I'm counting the electrons controlled by the chlorine. It gets 1 of each of these bonds, 1, 2, 3, 4, 5, 6, and chlorine usually ends up having 7. It's shy of 1 electron, so I would give it the formal charge that we expected, a +1. Your formal charges should be minimized. There might be a better method of drawing one of these, and I'm going to pull that one up right now. Here we've got another possible Lewis dot structure. This one has a triple bond between the carbon and the nitrogen. We have 2, 4, 6, 8 around the nitrogen, 8 around the chlorine, and 8 around the carbon. This structure is a valid one. Let's check its formal structure. Using the pair of electrons that nitrogen has here, we can make a triple bond for it. So we'd have 2, 4, 6, 8, but only has one of these electrons. So we have 1, 2, 3, 4, 5. Formal charge of 0. Okay, that's good. Our carbon here still has 1 electron in each one of these bonds, so indeed we give it a formal charge of 0. That's fine. And now we'll do our chlorine and see if our chlorine, well, we should know that if things add up to 0, chlorine should be a 0. With this count, I've got it so that the chlorine has 1, 2, 3, 4, 5, 6, 7, and here's chlorine in the halogen group with 7 electrons. This is a much preferred system. We've got a formal charge of 0, so this is most likely a very, very good drawing. And if you were asked to come up with one with a formal charge, this would be it. Triple bond between the nitrogen and the carbon, so all of our formal charges work very nicely. Chlorine typically ends up having 1 bond, and nitrogen typically has 3 unless we're providing some stress. So there we go, formal charge. And if that was it, you could stop the problem. But could be another question that said, what's the hybridization of the carbon in this molecule? Now, hybridization is part of AP, and you should know that AP, that if you have 2 sigma bonds, you have a linear molecule, and it's referred to as sp hybridization. Each one of these shared pairs of electrons is referred to as an sp. And if we had 3 sigma bonds, we would have sp2. So a good way of remembering that is imagine a superscript 1 and a superscript 1 on the S and the P, which means we have just 2 bonds. And here with sp2, a superscript of 1 plus 2 gives us 3 bonds, and of course our sp3 would be sp3 hybrid orbitals. Hybrid orbitals are very useful in organic chemistry, and you're expected to know them in AP. This is carbon is sp hybridized with two sp bonds, and it would end up being linear. And here's our diagram, nitrogen being a little bit smaller than our carbon, which we'd expect because as we go from left to right on the periodic table, our atoms tend to get smaller. There's a couple of exceptions in here, but that would be fitting that trend that we expect. The sigma bonds are our first bond that we have in covalent bond. Bonds that come after that, the double and triple bond, are referred to as pi bonds, and you should know that pi bonds are a little bit different in that they aren't as simple as a straightforward bond. Now, here's our sigma bond where we just have one orbital overlapping another. The pi bonds, the double and triple bonds, tend to be p orbitals that overlap and create sort of a cloud of electrons around the atom. Pi bond is weaker than the sigma, but of course together the sigma and the pi's make a stronger bond. These are called pi bonds, and they're around the atom. They prevent rotation. There we go. We've got our Lewis diagram for cyanogen chloride. We've determined its shape as being linear, 180 degrees between the nitrogen, carbon, chlorine. As a linear molecule, we'd expect some symmetry, but this is unsymmetrical because this chlorine has a different electronegativity than this nitrogen, and also we've got a difference in bonds. So this is going to be an unsymmetrical molecule because of the chlorine and the nitrogen being different, throwing our symmetry off, and this indeed does have a dipole. Dipole moment, I believe, is an area of 2.8 debye. So if you're asked to see if this molecule would end up having just London dispersion forces or a permanent dipole, this would be a permanent dipole.